Welcome. We are going to practice solving differential equations with an integrating factor. What you're going to need to know in order to be able to do this is that your differential equation must be linear and in particular take this first order form here. And so this is y prime or dy dt plus some function p of t times y equals some function g of t. If you can put it into this particular linear form, then you can get an integrating factor as shown on the bottom here, which is your integrating factor is mu of t equals e to the power of the integral of p of t dt. So this will give you the integrating factor. Now I have the theoretical development here that I'll just briefly go through, but it's here for you to look at your leisure. The general idea of an integrating factor is that it is some quantity such that if you multiply your original differential equation in this form by that quantity, by mu of t, it's going to help you actually solve it. And so the next tricky step is that on this left side, after you multiply through by mu of t, this left side is equivalent to d dt of mu of t times y. And you could check that, and so the derivative of mu times y is going to be mu prime times y, which you've got over here, plus you've got mu y prime. So here's mu y prime. So mu prime times y is supposed to give you this part here. And so that means that mu prime times y, your y's are there, so mu prime must equal mu p, which is what I say over here. And so this is a differential equation, and when you solve for mu, this is what you get in the end. And so let's go ahead and actually practice applying this. Here's the first example that we're going to tackle. So we've got an equation that is not separable, and so we need a new approach, but it is linear. We've got our y prime, and then our p of t is going to be -2. So take note that the original form is y prime plus p times y. And so you do need to account for negativity if you have it, which we do in this case. And our g of t function is the right-hand side, which is t squared e to the 2t. So since we satisfy the linear condition, we can get an integrating factor that's given by e to the integral of -2 dt, which is e to the -2t. So this is our integrating factor. So in step 2, we want to multiply our equation through by this integrating factor. So that is going to give us y prime e to the -2t minus 2y e to the -2t equals t squared. So e to the 2t times e to the -2t is e to the 0, which is 1. So that's why I don't have an exponential on the right-hand side. It's at this point where it's important to note that this has now become d dt of y e to the -2t. So that must hold. The left-hand side, after you multiply through by the integrating factor, must become the derivative of the product of your dependent variable times your integrating factor. So let's make sure that it actually holds. So the derivative of this is going to give us y prime times the exponential, which is our first term, plus y times the derivative of this exponential, which is -2e to the -2t. And so this is true. And this is equal to t squared. So now I want to integrate both sides. So we're integrating with respect to t. So the integral of a derivative is just the integrand. So on the on the left, we have y e to the negative 2t, and on the right, we have 1/3 t cubed plus c. And what's left now is to solve for y. So I'm going to multiply through by e to the positive 2t, and I have y of t equals 1/3 t cubed e to the 2t plus c e to the 2t. And so it's important to put your plus c in that previous step and not to add it at the very end here. So that's our solution to problem 1. Let's get some more practice and take a look at problem 2. So over here, we have another case that is not separable. It does look like it is linear, where p of t is 1/2 and g of t is 1/2 e to the t over 3. So this means that our integrating factor is e to the integral of 1/2 dt, which is e to the t over 2. So we multiply through, and that is going to give us y prime e to the t over 2 plus 1/2 y e to the t over 2 equals 1/2. Now e to the t over 3 times e to the t over 2 is e to the 5t over 6. So that's 1/2 plus 1/3, which is going to give you 5/6. Now this left side again is d dt of y e to the t over 2. And the right hand side stays the same for now. Next step, we want to integrate both sides. On the left, we have y e to the t over 2. And on the right, we are going to have 3/5 e to the 5t over 6 plus c. So there was this 1/2, but when you integrate e to the 5t over 6, you get 6/5. And 6/5 times the 1/2 simplifies to 3/5. And finally, y of t equals 3/5 times e. So when you divide by e to the t over 2 or multiply by e to the negative t over 2, it gets you back to t over 3 plus c e to the negative t over 2. So this is our solution. We do have an additional part to this problem, which is to make sure it satisfies or passes through the point 0, 1, where 0 is t and 1 is y. So we could continue and make use of that. So we want to know y at 0, that's going to be 1. So when we plug in 3/5 times e to the 0, that's 1, plus c times e to the 0 is 1. So when we solve for c, we're going to get 2/5, which means that our final solution is going to be 3/5 e to the t over 3 plus 2/5 e to the negative t over 2. Now this first solution is called our general solution. whereas the second one is our particular solution. Right, so general is when you have constants still there, and when you've solved for those constants, it's then referred to as a particular solution. We have one more problem to look at, so let's take a look at number 3. And for this third problem, it isn't quite in its linear form. So this one, we first have to make sure it satisfies that form. So I'm going to divide through by the t that is multiplied by the y prime. So dividing by t is going to produce y prime plus 2 over t times y plus, or equals 4t, and where p of t is 2 over t and g of t is the 4t. So now I'm ready to find our integrating factor. So mu is going to be e to the integral of 2 over t dt, which is going to be e to the 2 natural log t, which is e to the natural log of t squared, and by exponential and log relationship simplifies to just t squared. And so that's our integrating factor. When we multiply through, and you're multiplying this form after you put it into that general form. So when you multiply through, we've got t squared y prime plus 2t y equals 4t cubed, which is equal to d dt of t squared y, and that equals 4t cubed. So now we want to integrate both sides. So on the left, the integral of a derivative is itself. So again, we've got t squared y equals, on the right, we have t to the 4th plus c. And finally, when we solve, we've got y of t equals t squared plus c t to the negative 2. It's fine to write that as c over t squared. Either form is appropriate. And so, again, this is our general solution. This problem also came with a condition that y of 1 equals 2. So let's make use of that. So y of 1 equals 2. So at 1 squared is 1, plus c times 1 to the negative 2 is c, which means that c is 1. And so our particular solution is going to be y of t equals t squared plus t to the negative 2. And again, this is our particular solution. And as we did last time, here are some problems to practice at the end.